Okay, so now let's define the linear mixed model formally, and we'll do so in its general form. So the linear mixed model for a response measured longitudinally takes the form yi equals xi beta plus zi bi plus the random error epsilon I. Here, yi is an ni-dimensional vector of observed responses for subject I, xi and zi are design matrices, xi for the fixed effects and zi for the random effects. Beta is a vector of k unknown fixed effects, and bi is a vector of p unknown random effects. So the linear mixed model then is decomposing the response into three components, one fixed and two random. First, we have the fixed effect part, xi beta. This captures the population mean of yi. Second, we have between subject variation. This is captured by the random effects part, zi bi, and then we have within subject variation, which is captured by the error vector, epsilon I. So note that the design matrix Zi for the random effects is a known matrix of fixed predictors, something that we observe, often specifying membership of groups or subgroups, for example, in a hierarchical data structure. Now in the Gaussian linear mixed model, which we're going to focus on mostly in this lecture, the random components are assumed normally distributed. So the random effects bi are normal with mean 0 and covariance psi, shown here. And the errors are normal with mean 0 and covariance lambda I, where psi and lambda I are positive definite covariance matrices, and bi and epsilon I are assumed independent across subjects given the covariates. Now, given these assumptions, what are the mean and covariance of the response? Well, it's stated here in this theorem, the expected value of yi is xi beta, the fixed effects part, and the covariance of yi, which we're going to call sigma I, is zi psi, zi transpose plus lambda I. So the covariance has two parts. It is a between subject part coming from the random effects and a within subject part coming from the error term. That's that part there. And I've included a proof on the next slide of why the mean and covariance in the Gaussian linear mixed model take that form. To make this concrete with the Oxford data, the linear mixed model formulation uses xi equal to zi, so xi and zi are both the same design matrices, both containing an intercept and standardized age. That's all we have. If the intercept and slope random effects are normal with their respective variances, then the error is normal with constant variance, and the random effects are independent of one another. Then the covariance structure takes the form shown at the bottom, given here, sigma squared b naught times the identity plus sigma squared b1 times xi transpose plus sigma squared epsilon times the identity, this expression here. So the covariance of the response depends on the structure of zi and on the various components, and on the various components as shown here. I'll just take you through this slide briefly, since it's short. This slide gives the proof for the mean and covariance in the Gaussian linear mixed model. You can verify it in your own time, but essentially what it's saying is, for the mean, take expectations through the model. The random effects and the errors both have zero expectations, so we're left with xi beta, simple as that. For the covariance, the fixed part contributes nothing. The covariance of zi bi plus epsilon I gives the independence of the two random components. That is zi times the covariance of bi times z transpose plus the covariance of the error term, which just gives us this expression there.